So first of all, thanks Lauren Tak for inviting me today to tell you a little bit about my research. And let me start by thanking the people who actually did a lot of work on what I'm going to present today, Claudia and Valeria. Claudia is a PhD student at UNSW who is working with me, and Valeria is an undergraduate student at Columbia University who has been working with me remotely over her summer break. So today we're talking about materials for water purification. And I always like to start my talks with very big picture motivation. So we all know that everybody, no matter where they are, should have access to clean and safe water. And this is a fundamental human right. However, all over the world, we have severe issues with water scarcity and contamination for a variety of reasons. And this is actually true also for well-developed countries, such as the United States and Australia. And actually, very sadly, in these countries are typically the poorest communities to be the most affected by these issues. And so it's absolutely imperative that the scientific community works towards strategies to fix this problem. And there are a bunch of technologies that we can use to deal with water contamination. And one of the most common one is adsorption, where we essentially expose the contaminated water to an adsorbent, such as activated carbon, so that the contaminants are trapped and the clean water can get through. And this is, for instance, the technology that is used in the water pitches a lot of us have at home. But unfortunately, adsorbents like activated carbons are not specific to target certain contaminants, for instance, toxic heavy metals. So we really want to work towards finding new materials that we can tweak to capture specific contaminants such as heavy metals. And in this context, metal organic frameworks are extremely promising. These type of materials have this really cool 3D network that leads to very big pores represented here by these balls. And so this leads to really high porosity, really high surface area, which is obviously extremely attractive for an absorbent material. And in addition, these materials have these really nice organic looking functional groups here that can be functionalized so that you can truly target a specific contaminant so that the functional group will bind to that contaminant. So obviously, these materials are extremely promising for this type of applications. And in fact, the literature is already showing a very interesting report with MOF being used to capture contaminants from water, or even actually capture water from the air, which is another fascinating aspect I'm working on in another project. But today we're focusing on a specific MOF called UIO66. This MOF is extremely stable in water, obviously an important feature given the application of interest. And the crystal structure is shown here. It's always very challenging to show a crystal structure in a 2D picture, but essentially we have these metal oxide zirconium nodes, which are interconnected by these organic linkers called BDC. And even if this is very stable, very crystalline solid, it is very common to have some defects in this solid because some of these linkers might go missing. And if some of these linkers go missing, essentially what you end up with is some of these zirconium atoms represented in green here being undersaturated. And so basically what will happen is whatever is sitting around will go and saturate those sites. And this could be water, could be a chloride ion, could be another carboxylic acid. It all depends on the synthesis conditions. So lots of defects might be there, and the defects could be extremely different. So this is the MOF we focus on, and the contaminant we focus on today is arsenic, which is absolutely ubiquitous, unfortunately, in water, and this is due again to many different causes. In Australia, certainly mining contributes a lot to this, and this is something I learned more recently, but even the ash from the bushfire, so very, very important water contaminant for Australia. And this can have absolutely detrimental health consequences for human beings. And actually, the most toxic form of arsenic is its inorganic form, and this is what's present in drinking water. And because drinking water is oxygenated, we will have the highest oxidation state for arsenic, which is arsenic 5. And so if we take the pH of drinking water to be around 7, essentially the species that we expect to be around and that we will be modeling are dihydrogen arsenate and hydrogen arsenate. Now, there are a few reports, like I mentioned, in the literature showing that UIO66 can effectively use to remove arsenic from water. And the performance is quite outstanding. In fact, at low pH, it has been shown that it actually can get more than a higher 1 order of magnitude of arsenic out of water relative to what activated carbon would do. And the performance is still quite good, even at neutral pH. Now, these studies are extremely interesting because they also look into how the defects specifically affect the performance. And they found that the more defects, the better. And also the bigger the pores in the MOF, which can be achieved in different ways, the bigger the pores, the better the performance. The nice thing from the computational perspective is that these studies also use some IR spectroscopy to actually figure out how the arsenic is interacting with the MOF. And what they see is that essentially some zirconium oxygen arsenic bonding is being formed, which would most likely be formed if one of these linkers is kind of kicked out of the structure, and then the arsenic can come in and use 2 of its oxygens to coordinate the zirconium atoms. The other thing that's observed is that these hydroxyl here, which is typically referred to as the mu3OH, is also being affected, and so it might be participate to the binding mechanism as well. So as a result of these observations, we have a bunch of different proposals for the mechanism, but not really a clear conclusion. And so that's where the computational chemistry comes in. And so our goal here is to really give a definite answer with respect to what the mechanism of arsenic capture by UIO66 is, so then we can help our experimental colleague to build an even more efficient adsorbent for this species. And the questions I'll try to target today are essentially, again, what's the actual mechanism for arsenic capture? What species of arsenic is most likely to be captured around the pH of neutral water? And whether also some maybe weak interactions between arsenic and the MOF can contribute to the capture of arsenic. So as I mentioned, we're talking about computational investigation here. So these are some very quick computational details, but essentially we're just doing DFT calculations within ORCA. All the details are provided here, but to kind of have results that are somehow comparable to experiments, we do run frequency calculations, not only to ensure that we have minimum structure, but also to have some thermal corrections for the room temperature binding energies. And also we attempt to account for the presence of the water obviously in the MOF by using implicit solvation. Now, with respect to the modeling, the big questions you guys might have is how are you actually going to model the MOF and achieve a high-level density functional theory calculations? And the way we deal with this is we start with our optimized periodic structure. And then we cut out of the structure the kind of like the fragment of interest, which, as you might recall from the previous slide, is mostly the metal node. So we cut it out, and you can see here that the BDC linker have lost their carboxylic group, but that means that I would have had like a dangling bond, and so I just saturate this dangling bond with hydrogen atoms. And then actually we go and reduce further the size of the cluster to really just have what we really need, which is just one of these kind of two zirconium atoms that can be exposed upon removing the linker and can then interact with arsenic or other species around in the environment. Now with this cluster model, we then, during optimization, we keep all the capping hydrogens fixed so that it kind of simulates the constraints that you would have in a real crystal. And also, this is a little trick, but we also freeze the bottom of the cluster to save some more computational time, because these are quite expensive calculations. And then once we have this nice model, we can actually play with it, replace the BDC with like water to simulate, for instance, a very commonly found defect when water is around in UIO 66. And in the following slide, I'll just represent these nice defect site in a much simpler way for convenience. So what binding modes are we looking into here for arsenic with this defective UIO 66? So we can hypothesize that arsenic might come in and bind in a monodentate fashion, where one of the oxygen interacts with one of the zirconium, or perhaps just one oxygen might interact with both zirconium atoms at once. The other option is to have bidentate binding modes, where two oxygens join in and bind to either one zirconium or to both zirconium atoms. The other option proposed in the literature is that instead of having the ligand being displaced, we might actually have these mu3OH species being displaced, and then arsenic comes in and saturates the zirconium in its place. Or maybe we can have sort of like a mixed mode here, where both the ligand and the mu3OH get displaced, and arsenic comes in and forms three strong zirconium oxygen arsenic kind of bonding groups in a tridentate fashion. Now we have all these options that we need to look into, and how are we going to decide which one is the most favorable one? We're going to calculate reaction-free energy or a binding energy for arsenic to bind in all these different fashions. And this is just done like you would expect by taking the free energy of the products, the MOF bound to the arsenic, and the ligand that was displaced, and subtract the energy of the reactants. And so just like you would expect, if you see reaction-free energy below 0, that means that the reaction is favorable, and the more negative it is, the better. The other big question about modeling this reaction that I want to quickly bring up is that we're displacing a ligand, and this ligand is an anion. Okay, so we're releasing an anion, and depending on the pH conditions and also depending on our model, releasing an anion might be making this reaction artificially unfavorable. And especially given the pKa of water, which is 15, you can probably guess that it would be much better if we could protonate this hydroxide and produce a water molecule instead. And so this is exactly what we did. And we used two different options here, which have different advantages and disadvantages that I don't have time to discuss. But essentially, we tried to protonate hydroxide either by taking a proton from the arsenic, and so forcing it to get the protonated in order to bind. And then also we modeled an explicit proton. So with this, I'll show you just the kind of complete analysis that we did for dihydrogen arsenate here, and all the binding modes we've looked at so far. And you can see that overall, we have these monodentate mode, bidentate mode, and these tridentate are probably the most favorable modes we can see. But in general, the bidentate is definitely the most favorable by about 10 kcal per mole. But the questions we had actually in addition to this type of analysis, came up after we looked at the monodentate mode a little bit closer. As you can see here, there is a nitrogen bond being formed between the arsenic species and the water molecule. And so we wonder whether maybe we could use a similar hydrogen bond to actually stabilize two arsenic species at once, because that would be amazing for absorption performance if given one site we can get two arsenic trapped instead of one. And so, we were really happy to see that this actually can happen, and it's favorable by 14 kcal per mole to kick out this water molecule and place there a second arsenic species. And so, if we try to think a little bit more about the experimental system, I think what we can conclude is that if we are in a condition of like low diffusion or small pores, so very few arsenic can be in a pore, then it's most probably only one arsenic molecule will absorb, and will absorb in the bidentate fashion, just taking over both sides. But if we are in a high diffusion regime with big pores where more molecules can be exposed, we can be in contact with the site, then we might be lucky and we might get a kind of double monodentate absorption mode, which again might help explain why the MOFs with bigger pores had a better absorption performance. It might not just be about diffusion, it might be about the size of the pores allowing more molecules to be in the vicinity of the defect site. And obviously these two things are kind of interconnected. So we then did a similar analysis for the other arsenic species, the hydrogen arsenate. I'm not gonna go too much into details, but I have a summary here for you. And the first thing you can see here is that obviously the doubly deprotonated anion here has a much stronger binding energy, which is not surprising, okay? But the other interesting thing to observe here is that we can again, if we're thinking about, high diffusion regime with a lot of molecules around, we can again expect that we will end up with the double monodentate to dominate here. But the problem comes in case we have a lower diffusion. In that case, we can only have one molecule binding at a time. And if we are at a high pH with hydrogen arsenate dominating, it's likely that these will end up in a bidentate mode, because the bidentate is more stable than the monodentate by 20 kcal per mole. So it might actually be safer to be at a lower pH where there is a smaller difference between the bidentate and the monodentate. So we might have a chance at getting a monodentate absorption that would leave space for a second arsenic to absorb and maximize absorption performance. So based on this result, we kind of expect that the optimal conditions here are to have a low pH and to have very large pores to allow for hopefully this double monodentate absorption. So the last thing I'm going to talk about today, and I'm going to finish soon, is the role of weak interactions in this absorption process. Another thing we were excited to see is that this newly proposed absorption mode with this double monodentate structure both show hydrogen bonding to this mu3OH group, which you might recall was indeed observed to be affected in the experiments. So this new structure also agrees in the experiments in terms of these IR observations. In the literature, there were a bunch of other options suggested to explain the mu3OH being affected. One of them was a simple hydrogen bond from an arsenic molecule in solution, but we can see that an hydrogen bond with arsenic relative to an hydrogen bond with water is now more favored. So it's more likely that if there is an hydrogen bond to be formed, it would just be with water. So it would not explain that the changes observed with this mu3OH. And the other option was some sort of bidentate mode where the proton from the arsenic kind of reach an hydrogen bond to the mu trio, but these also, it doesn't seem stable based on some preliminary results. So to conclude, in the double monodentate seems to explain, like I just said, also these additional IR observations with the mu3OH being affected. So overall, what I showed you is that we can definitely confirm the experimental findings that the defect sites must be playing a big role in arsenic absorption. We did find that it should be favorable to absorb 2 arsenic at once in a defect site, which would explain actually a lot of the experimental observations. And overall, we believe that a lower pH and larger pores should maximize absorption performance. We're also working on a few other aspects, like what happens if instead of having this type of defect site, we try to use different type of defect sites. We're also looking into using these defect sites to absorb other type of contaminants, such as toxic heavy metal ions. And ultimately, what we want to do is also do some molecular dynamic simulations to truly model the diffusion that I've been discussing in the talk. So with that, big thanks again to Claudia and Valeria for their hard work on the project. I have to thank all the computational facilities that have given us a lot of computational time, both from NCI and from UNSW, my collaborators who I work with on the water capture project at UC San Diego, the Scientia Fellowship Program UNSW for supporting me and my research, and of course, again, Laura and Tak for inviting me to speak today. And all of you for listening.
Thank you very much. I'll clap on behalf of everyone.
Thank you.
Okay, so what I wanted to do was give us a moment for students to ask questions in the chat. So I might give us a minute or so, and then I'll go to some other questions. I just want to, I know it's hard for students. It takes a bit of time to think of a question.
Yeah, of course. Totally.
And to type it up. So the sort of questions, I mean, motivation. So there's lots of, you can ask about the computational stuff. You can ask about the way that she is sort of organizing her research. I asked a question about, like a lot of the questions from, some of the people that are in this field are a bit more technical, but also feel free to ask about the science aspect of things. So how do you actually do it in practice?
Definitely.
Okay, so I might start with some of the questions. Peter Canfield asks, have you looked at the possibility of condensation of the double monodentate mode to a peroarsenate?
No.
I'm not sure I know. Peter, I can unmute yourself if you want to correct my wording. Can you see the questions in the chat, Martina?
I am not looking at them right now, but I'll exit full screen and I think I should be able
Peter,
to see.
did you want to clarify that?
Chat. Oh yeah.
So you've got your 2 arsenates sitting there right next to each other, and they're at a low pH and they're protonated.
Yeah.
Certainly with phosphate, you'd expect those to condense with each other, spit out water, and you get a phosphate, or in this case a pyroarsenate, where the 2 arsenics are linked by one of the oxygen atoms. So you'd form this cyclic system.
Yeah, we haven't looked at that, but that sounds really relevant. So we might look into that.
Yeah. You said the experiments, some of the experiments show 2 arsenates binding. I wonder if there's been any things like Mossbauer spectroscopy or anything like that.
I haven't seen that, but now that you're mentioning this specific type, I'll look into it.
Okay, cool.
Thank you.
Excellent. So that sounds like it started a new research direction, which is awesome.
Yeah.
So, well, except when you want to get out the paper, in which case next paper. Barris Demir asks, what is the role of the organic linker in absorbing arsenic? For example, if you functionalize the organic linker by, say, adding an amine group, how would this alter the absorption properties of the MOF?
Yeah, that's a great question. So actually this has been done, but more for like heavy metal cations like lead or cadmium or mercury, who would be, you know, really be happy to be like coordinated by a amine group. But in one of the studies I discussed, they actually also look at the absorption of arsenic-3, not just arsenic-5, which indeed really likes to interact with like an amine group, or I think in that case they use thiol functional groups, and so they took UIO66 and placed thiol functional groups on the benzene, and then did see that improved the absorption performance for arsenic-3. So yeah, that's definitely one of the directions we're looking into. Yeah, I hope I answered.
Cool. Terry asks, what was the water rate through these MOFs? There was mention of diffusion in the talk, but was a bit...
Sorry, you said the water rate?
Water flow rate through these MOFs.
Oh, I don't, so I guess you're thinking of like an experiment where you're kind of like pushing it through the MOF filter, but I don't think these experiments are already at that level of like having an actual like membrane or filter. It's more of like throw the MOF in the water solution, mix it, and then see what comes out afterwards. Or the other thing they do is they actually do like absorption isotherms for the different contaminants. And I'm not sure whether the water flow would matter there.
Excellent. We've got another question from Rohan, a student, which is awesome. Do you know how the adsorption energies of these defect sites compare to the MOF sites that are not defects, i.e. still have the linker attached? Is there available arsenic absorption at the sites?
Yeah, that's also a great question. So I didn't have time to show this today, but we've actually, we're looking at how the absorption strength compares when we have different type of defects, or the pristine MOF with the BDC linker sitting there. And actually, it looks like it's very much more difficult to remove the BDC linker as opposed to like a water molecule and an hydroxide. So although some of the experiments have proposed that absorption might occur by BDC linker displacement, we think that would be rather unlikely because it doesn't seem to be energetically favored.
Excellent. There's a few other questions, but I might just leave them till the end so that we, oh, you're not going to be here.
Yeah. Sorry, have to teach.
No, that's all right. Well, I'll just do it quickly then. Have you benchmarked with larger, less truncated models?
No, we have not. I think going to the next level would mean like a much bigger cluster, and that might be just basically unfeasible, because one of these free energy calculations already take like about a week in best case scenario, which is a lot of computational time. And so although I agree that ideally you want to do a benchmark like that, we might just have to be happy with what we have. Also, this type of cluster models for UIO66 have been used in other studies in the literature, and they seem to be working fine. So
cool. And just a quick question. I wonder how the thermocorrections work with constrained atoms. Is there a risk of having imaginary frequencies that are quite high?
Yeah, so definitely you gotta be careful with that. And so they're basically they're not excluded from the thermal calculations, but there is kind of like a way to deal with it that accounts for the fact that they're not in a minimum position. And so you don't end up with imaginary frequencies. Yeah.
Excellent. Okay, well, I might just ask Siobhan, who is in the wrong, her name is currently, we had some technical issues, so we've got a different name up, but thank you very much, Martina.
Thank you so much.
I know Claude is definitely in the audience to help answer some questions later on, and Martina is happy to take emails, I'm sure.
Absolutely. Thank you.
See ya. Siobhan, you ready?
Yes. Can you hear me? You can hear me all right?
Yes, we can hear you all right. We can see your screen.
Okay.
Now we just need a PowerPoint or something.
Yeah. Okay. It has gone somewhere. Oh no, here we go. Yeah, cool. Okay.
Excellent.
All right. So hopefully you can see this.
Yep, no, it's perfect.
You can see that? All right.
Good to go.
Cool. All right. So sorry about those initial technical issues. So my name is Siobhan Bradley, but for today you can call me Faye. And I think I'm coming to you from one of Faye's holidays behind me. I'm not sure if you can see this, but yeah, so I'm from the University of Melbourne, and it's nice to have a break from wearing a face mask for a little while. So thank you to the organisers. And thank you also to, I've got two colleagues who are in the chat, Dr. Christopher Hall and Kyra Schwartz, and they will both answer any questions that might come up during the talk. And they're friendly, so don't be afraid. So today I'm going to be talking about a series of systems based on the chromophore diketopyrrole, which I will call DPP from here on out. And I'll be talking about the photophysical processes that are occurring in these molecules and in these different systems. So the context for this type of research is that I think we can all accept that global energy demands are increasing year on year. Interestingly, in the last couple of months, there's been like a 20% decrease for everyone working from home. But generally speaking, it's an upward trend. So you can design new technologies, or you can try and better the technologies that you have. So one solution in the solar energy conversion area is better spectral utilization. So we know that solar cells absorb the visible pretty well, and they absorb part of the UV, but not very well in the IR, and not that well in the UV. So one of the things that we can do is what happens in a solar cell is that the photons that are below the band gap of silicon are not absorbed. And then the ones that are higher, they lose some energy in what's called thermalization in order to get to the band edge. And so this is a loss process. And this is one of the things that limits the efficiencies of solar cells. But what we could do instead is try and utilize those high energy photons and convert them into twice as many photons of half the energy, or twice as many excitons of half the energy, and inject those into the conduction band. So that would be a very nice solution. And how you would do this is through a photophysical process called Singlet fission. And so this is a process that takes one photoexcited molecule, so photoexcited to the singlet state, and then if you have another molecule nearby, and these molecules are coupled together, so then you can form what's called a correlated triplet pair, which is this thing in the middle, and eventually form two independent triplets. And so the reason that this process can happen quite efficiently and quite rapidly is that the two triplets are coupled together in a way that they're like an overall singlet, so it's not spin forbidden. And so the requirements for molecules that can undergo this process are that they have a triplet state that is roughly half of the energy of its singlet state. And so that means that compared to a lot of molecules, the triplet energy has to be quite a bit lower. And there are a few molecules that conform to this, so groups of molecules. And they are the alternate hydrocarbons, like the acene. So there are some examples here, like tetracene and pentacene and their derivatives. And they've been studied quite extensively. And then there are biradicaloid molecules, although most of these molecules need some kind of biradicaloid character in order to accommodate two triplets on the one molecule. And so, yeah, it requires two chromophores at a minimum. And so you can imagine that the absolute smallest system that you can study would be a dimer of these two chromophores. Or you could look at intermolecular singlet fission in things like nanoparticles and thin films. Yeah. So this schematic here is pretty nice. It's just showing you that there are some systems where the correlated, twice the energy level, twice the triplet energy is higher. There are some systems where it's roughly equal to, and there are some where it's lower. So it means that you can have endothermic or exothermic singlet fission. And if you think about that, endothermic is pretty attractive because it means you can also harness energy from your environment. Whereas in exothermic, you lose a bit to the environment. So there are all kinds of different strategies that a lot of different groups around the world are taking to tackle this problem. So the state of the field at the moment is that most of the singlet fission studies are dominated by tetracene and pentacene. And a part of this is because, I mean, there's a huge body of research behind it. And the triplet is quite easily observed. It's in a region that's quite easy to see over all of the other things that can be happening in usually the visible range. And I've seen close to 200% efficiency in TIPS pentacene derivatives. And these have been good studies, good systems to study to look at the singlet fission mechanism, which is still not 100% defined. And also a lot of the fundamental studies are in dimers where you can study them in solution. So you can probe things like charge transfer states because they will be dependent on solvent. So the dielectric environment can change how those states form. And in terms of applications, so getting closer to, you know, this dream of solving the world's energy problem, energy problems. You have, there's a group already, oh, I think this is on a timer, damn it, okay. So there's a group already that has reported a solar cell with an internal conversion efficiency of 133%, so that was 6%. And then there are lots of examples where people try to either sensitize other materials like semiconducting materials or perovskites and so on with a singlet fission layer to see whether you can inject triplets into those materials or the other way around, kind of trying to understand how energy transfer and electron transfer can happen between these materials. Okay, so yeah, there's been a lot of study on these two particular chromophores, but you know, if we want to be able to apply them in all kinds of different systems, so not just silicon solar cells, then we need to have a diversity of energy levels. And so we need a diverse range of molecules. And so one such kind of more alternative chromophore is diketoperol. And it has some very desirable characteristics like being photostable, which you can imagine in a solar energy conversion process is pretty important. It's air stable, it's highly absorptive, has a high quantum yield, it's solution processable, and you can modify the kind of energetic structure through these groups on the molecule that can extend the conjugation. And then also you can change the solubility by changing these solubilizing groups here on the nitrogen. So yeah, it's pretty attractive as a chromophore. And we know that it has this energy level structure where the triplet energy is roughly half of the singlet. And it's been shown to undergo singlet fission in thin films, and that happens through a charge transfer state. So it's kind of interesting to look at. So the systems that I'm going to be talking about are so monomers, dimers, nanoparticles of both of those things, and films. And just the important thing is that there's a difference between the bridge between the two chromophores and the dimer, and one is a kind of more flexible. So I'm calling that a C5 linked dimer. And then there's a xylyl group in the center for the other dimer, which is a kind of more rigid system. And I also have their monomers as kind of control molecules. So we'll have a look at the photophysics of this dimer system, and then later talk about what happens when you put them in a nanoparticle or a film. So when you go from the monomer to the dimer, the first thing that's very obvious is that there is some quenching of the fluorescence. So here I'm just showing the fluorescence lifetime, and that in both of the monomers, the benzyl and the C6, they have mono-exponential decay. So that's an indication that the excited state is being depopulated by fluorescence in this case, and that's the only process happening. But you can see that it gets more complicated and further from single exponential when you look at the dimers. And so what that indicates is that where normally you would just have an emission process depopulating the excited state, instead there's this new state that can form that is quenching that fluorescence process. And we want to know what that is. And if it's not radiative, then we have to look at other techniques to identify it. So what we use is transient absorption, and I thought I would just give some general features so that you'll be on board for the rest of the talk. So here we have a transient absorption spectra of one of the monomers in toluene, so in a not very high dielectric solvent. And here I've put the absorption spectrum over the top and the emission spectrum over the top, so you can see what they relate to in the transient absorption. So first you have what's called the ground state bleach, which should mirror the absorption spectrum. So that's just saying that you're depopulating your ground state. And then you have your stimulated emission. So that's like your fluorescence, and it's letting light out. And this is a change in absorption over time. So it also looks like a negative signal. And then any positive signal is the absorption spectrum of the excited state. So just like running a UV vis, but on your excited state. So we can see here that something is absorbing wavelengths, and it corresponds to absorption from the S1 state. So just tried to show that if you pump your sample up to the S1 and then you illuminate it with a second source, so your probe, then you can measure the absorption of that, for example, charge transfer state. So that's what we're looking at here. And then sometimes there are kind of weird squiggles that are to do with the pump scatter. So I'll try and point out when that's happening as much as possible. Right, so in the transient absorption, the main difference that we see in the dimers is that there's a new excited state absorption that forms here at about 640 nanometers. And this feature shows solvent dependence, so that indicates that it's something like a charge transfer state or a charge separated state, or something with a dipole, because it's affected by the dielectric environment. And so you can see here, so I've just got those two traces over the top of each other, but on a log scale, and you can see that they form at different rates depending on the solvent, so much faster in DMSO compared to benzonitrile. Unfortunately, we don't see long-lived signals, so the evidence for a triplet state would be that it lives a lot longer, you know, like you would know for phosphorescence. Unfortunately, we don't see that in this case, but we still kind of needed to understand what's happening that's competing with singlet fission. I could also see that the bridge has an effect on this quenching process. So, sorry, excuse me. So you can see that the kind of rigid dimer forms fastest and forms fastest in the most polar solvent, whereas that more flexible link dimer in the black forms slower and slower in the least, in the lowest dielectric solvent. So the bridge is definitely having an effect on this charge transfer process. Okay. So we think that that charge transfer state is acting as a trap, and I've tried to demonstrate it here. So if you imagine these different colors as being different solvents, that by having different dielectric environments, we're stabilizing this charge transfer state here so that it's below the correlated triplet there. And so then we rather have charge separation and we don't see singlet fission. And the thing about DPP is that these levels are very closely matched. So the triplet state is basically half the singlet. So there's not a lot of freedom, energetically speaking, to get around any barriers that might be present. So that was, yeah, it's a nice simple story, but actually it turns out that it's more complicated because as you might remember in that TCSPC fluorescence data, there was still emission. So that indicates that there's still some monomer emission as well as this quenching process. What other groups have explained it by is, so here's an example where there's a similar dimer, but where it's fixed into a coplanar. So the two chromophores are coplanar with each other configuration. They saw similar behavior, but they explained it by having a kind of a pseudo equilibrium between the excited state and the charge transfer state. So that you can go along this charge transfer pathway, but you can also go back to the first excited singlet state and fluoresce. But if this were the case, then we would see long-lived fluorescence. We would see fluorescence that was longer than the monomer alone, which is called delayed fluorescence. And we don't see that. So I don't think that this model is correct in our system. What I think is happening and what I'm trying to model at the moment is a system where we actually have a population of chromophores here. And those chromophores have different conformations where they are different distances from each other. And so the ones that are quite far apart probably act like monomers and just have normal monomer fluorescence. But the ones that are close enough together can have this charge transfer process happen and can follow that second pathway. So I'm modeling it with a bridged system where the molecules in the excited state can either take one pathway or the other, depending on what conformation they have. And that's a work in progress. Something that is kind of interesting is that in all of the systems where you see singlet fission in DPP, so mostly thin films, there's a low energy peak. So what happens when you have two chromophores in proximity to each other, based on Cash's theory of molecular excitons, is that they can couple in different ways. So if their transition dipole moment, which is the electric dipole along which a particular transition can occur, so kind of explains how it couples to light of a particular polarization and whether that transition occurs. They can either be here coplanar, so one on top of the other. And in this case, this is leads to a higher energy absorption peak called an H aggregate peak, or they can be head-on or slip stacked. This leads to a low energy peak. And what we've found is that there's always this low energy peak in examples where you see singlet fission in DPP. So it might be indicating that that particular structure is quite important in order to have this process occur. You can see here that in the monomers and the dimers, we don't see a low energy peak. So it's more likely to be in this H aggregate configuration compared to in films and nanoparticles. I also just wanted to say that we had a colleague here at the University of Melbourne, Dr. Lars Gehrig, and he did some ground state calculations for us. And so this is DFT calculations that incorporate London dispersion forces. So in a molecule that has a dipole like this and where these interactions, these pi-pi interactions are pretty important, you have to take into account these forces. And he showed that all of the dimers are folded in the ground state, but that there are a lot of different conformations that are thermally accessible. So it's very possible that there are a range of different conformations and that this kind of broad heterogeneous model that we proposed before could be right. Okay, so the next question is, can we force the molecules into that conformation? So can we force them to go to J aggregate? And we can do that. So what I did was I tried different methods of what's called reprecipitation. And this is a method that we use to make nanoparticles of chromophores. And that's useful because then you can look at a kind of pseudo solid state, but in a liquid medium. So you can do solution phase measurements. And so you inject the molecules in a good solvent, so something like chloroform, into a bad solvent, so something like THF. And these two solvents need to be very slightly partially miscible so that you can form these nanoparticles gradually, and the two solvents interdiffuse until you have particles which if you then evaporate off that good solvent, you can be left with a pretty stable aqueous dispersion of those nanoparticles. If you do this whilst providing some energy to the system, so I tried heating the system and sonicating the system with pretty high powers, I found that you can force these molecules into different conformations. And so the telltale sign is, again, going back to the UV vis. So I can see that when I make these nanoparticles of dimers and I heat them, then I don't see that low energy J aggregate peak. But if I sonicate them, then after about 6 hours, they start to form the J aggregate peak. So there's some kind of rearrangement that's happening within the nanoparticle, and then that structure remains relatively stable over time. And what I found is that in this case, we do see long-lived, a long-lived bleach. It's a bit of an absorption too, but we see that there are signals that could be associated with a long-lived triplet that we don't see in the like heated equivalent where you don't have that J aggregate peak. So that was pretty interesting. And then the last thing to look at was how this compares to thin films. And the interesting results from the thin films are that if you make a thin film of dimers, it appears that the bridge in the dimer seems to disrupt the packing. So we didn't see any long-lived signals indicative of singlet fission in the dimer films, but we do see it in the monomers. And this was despite the stacking distances between the chromophores being roughly the same for basically all of the films that we made. So that was an interesting result, which I still need to look into. I also found that it's quite different spectral behavior. Well, the spectra look quite different for the benzyl monomer compared to the kind of flexible monomer. And what's interesting is that, so here I have the bleaches of the two main bleaches in the transient absorption for each of these monomers. And in one case, the bleach that lives the longest, so the bleach that would be leading to the singlet fission process, seems to be in the lower energy bleach. And in the other case, it's in a higher energy bleach. And the significance of this is that the two monomers seem to show the opposite behavior. And if my theory that J aggregation was a requirement for fission was right, then this appears to suggest otherwise. So I haven't quite figured out what the significance of these two results are, but I knew that there'd be some photochemists in the audience, so I wanted to put that one out there for people to think about. So yeah, that was basically everything I wanted to talk about. So just to go over the main conclusions, I didn't see any singlet fission in the DPP dimers, and I think that that's because we have all of these different conformations, and that if anything, they'll take a charge transfer pathway compared to this option of singlet fission. And in DPP nanoparticles, I could see fission, but only when you trap these particular conformations. So that's obviously something that I'm focusing on the last couple of months, trying to understand why it is that those particular conformations are important. And then in thin films, it turns out that having a bridge between dimers actually works against you, and it disrupts what should be favorable packing. So we don't see singlet fission in DPP thin films of dimers. So you can see it's a bit of a complicated story, and it's a bit of an interplay between conformation, the coupling between the molecules. And then lastly, there's always this argument of entropy. So if you can form two independent triplets through this singlet fission process, they're more likely to form in a film where they have a range of different kind of areas that they can be in the film, and what places that the charges can reside. Whereas when you're in a dimer, you're fixed, you're stuck on the dimer, and it's very easy for two charges to then just kind of recombine and go back to the singlet state. So it's always a bit more complicated in films because of this. So yeah, lastly, I just wanted to thank everyone who had contributed to this work. So there's the synthesis people. That was a master's student who was working for Jonathan White at the University of Melbourne. And then Dr. Lasgerig did the calculations, and Taki, one of our hosts, and his postdoc, Patrick, helped with some of the long time measurements for the nanoparticles. And finally, wanted to thank my group. We've had a lot of discussions about this, and especially my colleagues who are helping out in the chat at the moment. I don't know if there have been any questions, but thank you all the same. Cool. All right, so that's me done.
Thank you very much. Okay, so I'm going to give it about a minute or so for questions. I understand if you need to run. I know there's meetings that go on all the time at the moment. Thank you very much for coming along. We'll give it a minute or so for student questions and then we'll get started. So let's start with Klaus's question. I was wondering what an IR source would do to the nanoparticles conformations. Heat lamp, maybe?
Oh, that's a good question. I had not thought about that. I assume that it could change their conformations. I guess it depends if there's still residual solvent, but you can see that. So I think in those examples I had up there, I measured those particles for up to a month. And still there was some obvious movement in the packing arrangements within the particles. So I imagine that any energy that you provide to the system could have an effect on how they're packing. Yeah.
Excellent. Jessica says, thanks, Siobhan. I might have missed it, but could you elaborate on how the sonicating heat causes the alternative nanoparticle conformation? Is it just the extra energy?
Yeah, that's a good question, because I think maybe the point you're getting at is that adding the energy could also evaporate that favorable solvent. So it could be that the effect of the heating was removing some of that solvent at the same time as giving the molecules enough time to move within that favorable environment. So the short answer is that I don't know which of the two or what combination of the two it is, but it's definitely possible that it could be both. Could be affecting the particles, in both of those ways.
Sarah Master asks, I might have missed it, but what would the ideal stacking distance and or offset of rings for singlet fission?
Yeah, so there's I guess there are a few papers that look at thin films and look at singlet fission rate as a function of...
I'm assuming that's not saying it, you're wrong.
They look at the singlet fission yields as a function of the distance between the chromophores, and it's about I think that it's about like 3 angstroms, but I guess it also depends. Like, it's not just the distance between chromophores. It's obviously, as I've kind of talked about, it's how the chromophores are arranged, kind of relative to one another. The angles, the distances, and the alignment. Yeah. Was there another part to that question?
No, ideal stacking distance and or offset of the rings.
Yeah, and then offset. And again, that's...
Oh, and Sarah, if you wanted to unmute yourself, you're welcome to, obviously.
Yeah.
Yep. Simon asks, when thermally forcing conformations in nanoparticle systems, have you checked if the products are stable over long time periods?
Yeah, so I think what I showed there was about a month, so showing that they're not changing much over a month, but you could see that the absorption was dropping over time, only slightly, but it was nonetheless. And I think what happens there is that, just particles will collide and they will form larger structures and then drop out of solution over time. So I do think that they're not perfectly stabilized in solution. So yeah, they would change over time. It's probably not an ideal solution that you would use in a device, but I do think that they're important structures because they're really the only ways that we can trap these different conformations that you can't really get in a thin film. You can in some instances, but it's just more complicated in a thin film.
Mm-hmm.
Yeah.
Samuel asks, from the first crossing from the S1 to the triplet, how much does the character of the states matter for these systems? Are there things like the L-Sayat rules like S1 pi star to Tn n pi star still relevant when you have multiple chromophores? It's in the chat if I didn't communicate that well.
Yeah, I don't know that I fully understand the question, to be honest.
Samuel, did you want to turn on your mic?
Hi, can you hear me?
Yeah, hey.
Sorry, that question isn't very easy to read, but
Okay.
I guess what I was wondering is you talked about how the energies should line up for the S1 to the triplet and those sort of things, but like thinking about the orbitals and whether that sort of like the character of the state, whether it's pi to pi star or n to pi star, like a pi to pi star character singlet going to an n to pi star character triplet, if that is favorable when you've got like when you've got, I guess, lots of things going on. I suppose that
maybe, I mean, is there anyone else in this singlet fission who's around who has?
So Jeff and Tak have some comments. See if they can unmute themselves.
Yeah, that would be cool.
So the chat says they are different processes, so there is no connection. Tak says there are two triplets, and Patrick says the overall process is spins conserving.
Patrick, would you like to take this one?
Real-time feedback.
It is nice. Yep, go for it, Tak.
Oh, I was hoping Patrick would take this one.
Oh, okay.
Maybe Patrick, can you unmute yourself, or are you not convenient?
Yep, no, he's come.
Can you hear me?
Yep.
Hey,
Cool.
Patrick.
I came in a little bit late, so yeah, I missed a bit of this talk. But if it's a singlet fission process, you have you have one singlet excited state, one singlet ground state, and then you have two triplet excited states. So the overall spin of the pair, the two chromophores or whatever, is still like an overall singlet. You're not violating any of those rules or anything like that.
Oh, right. So it's not, it's like technically not an intersystem crossing.
No.
Correct. Yep.
Okay. All right. I understand. Thank you.
Great question. I don't know if you've got any comments on how you get the silver nanoparticle dimer synthesis.
The silver nanoparticle dimer synthesis. That wasn't part of my research, but perhaps that's it.
Okay. Yep. I thought it wasn't quite. I think
so the dimer is like it's a bichromophoric dimer. So maybe I made that clear. Whereas those nanoparticles later on are nanoparticles of all of these chromophores stacked together, forming a kind of small solid.
Okay. Well, I'll just ask one more question from Almaz. Can you say more about the nature of the charge transfer state?
Yeah. Okay, so the charge transfer state, so there are kind of thought to be two mechanisms with singlet fission, and one is that it just goes direct from this excited singlet to this correlated triplet pair, or it could be that first it's mediated by a charge transfer state. So here you can see, you're excited, this is a singlet state, and then you get charge transfer, and that's the start of forming these two correlated triplets. Yeah, something I think I had it in it. This is a really nice review if you did want to read it, by the Gouldy group. But here you can see that, so once you've transferred that charge, right, and to talk about the difference between charge transfer and charge separation is that charge transfer, we're kind of talking locally, and then later charge separation is when they're separating onto the separate chromophores, and that's something that's spectroscopically observable. You can see the radical anion and the radical cation. But for this charge transfer state, they think that either the charge transfer state can be lower in energy, so it would act as a trap, preventing singlet fission, or it could be similar in energy, and it could be an important intermediate before you form here this correlated triplet pair. Or it could be that it's like a virtual state where you can't really observe it, but it is having a role in the process of forming that correlated triplet pair. So that's kind of the significance of the charge transfer state in singlet fission. And, you know, it's easy to observe because it's something that you can probe just by changing your dielectric environment. So, yeah.
Sounds cool. Well, thank you very much, Siobhan, for an awesome talk. I'll clap on behalf of everyone.
Oh, thank you. Thanks, everyone.
You know, good to have. Okay, so what we're going to do now is, thank you very much for the clapping icons. Yep, excellent. Okay, what we're going to do now is we're going to get a few of the people that have been here a while to introduce themselves, just to give you an idea of how we're going to go about this. And then we'll just give everyone a little while if they'd like to, and then we'll separate into breakout rooms.